In 1977, the Space Shuttle Enterprise performed its first low-speed flight trials. These unique flights made history. They were the first step in our ability to travel in space and return on a regular basis. The location of these flights was unique, too. NASA's Hugh L. Dryden Flight Research Center. Dryden sits on the edge of Rogers Dry Lake, a 65-square-mile expanse of tough, sun-baked clay. It has a rich tradition of accomplishment. It was the location of the world's first supersonic flight and first hypersonic flights, many of which also went into space. NASA's predecessor, the National Advisory Committee for Aeronautics, established Dryden in 1947 to test fly the X-1, the first airplane to go faster than sound. The center's personnel first proved that manned supersonic flight could really be done. They did it with the X-series aircraft, such as the delta-winged XF-92A Dart and the D-558 Phase 2 Skyrocket, first plane to fly twice the speed of sound. The X-3 found and probed dramatic roll stability problems in supersonic jets. And the bat-like X-4 researched pitching instability, which jeopardizes tailless airplanes. The X-5 was a variable sweep plane. It proved that such aircraft can fly. With wings extended, it excelled at low speeds. With wings swept, it performed well at high speeds. At the same time, the Air Force was flying the X-2, the first plane to reach Mach 3 and nudge the thermal barrier. NACA engineers designed their own advanced research plane based on the X-1. This was the X-1E. It could fly twice the speed of sound and had an experimental wing configuration. The X-1E now is mounted in front of Dryden Flight Research Center, a monument to those early years that gave the world supersonic flight. From 1958 to 1968, Dryden test flew the X-15. It was the first airplane to explore the region of aeroheating and fly above the atmosphere. It reached speeds of 4,500 miles per hour and got to altitudes of 67 miles. The X-15 pioneered re-entry from space to an aerodynamically controlled landing. Dryden's research extends to all kinds of airborne vehicles. To support the moon landing, our engineers designed the Lunar Landing Research Vehicle, which simulated a descending lunar module. Apollo astronauts practiced on these flying simulators before they attempted the real lunar landings. In the late 1960s, Dryden flew a test program exploring the characteristics of large supersonic cruise airplanes. The XB-70 contributed to the design of supersonic transports. One of Dryden's most exciting programs was the YF-12 Blackbird. Our pilots and engineers tested two of these aircraft in the late 1970s. The Blackbirds were capable of sustained flight at Mach 3 speeds and 80,000-foot altitudes. Our tests with the YF-12 studied handling qualities, high-temperature structure effects, and performance of the exotic turbo ramjet engines. NASA's Parasev explored the possibility of using flexible wings, which would allow returning spacecraft to land at conventional airfields. Results left a lot to be desired. And the idea was grounded. In the early 60s, Dryden began testing a group of aircraft called lifting bodies. The plywood M2F1 was the first, towed aloft by an airplane, then released to land as a glider. Half spacecraft and half aircraft, lifting bodies were designed without wings, so they might re-enter the Earth's atmosphere with a minimum of structural and heating problems. Success with M2F1 tests led Dryden engineers to develop the M2F2. In contrast with its light, unpowered predecessor, this craft was a rocket-propelled heavyweight. The M2F2 demonstrated that this shape can fly at the high speeds representative of vehicles entering from space. The HL-10 represented another lifting body design approach. Like the M2F2, the HL-10 was a heavyweight vehicle equipped with rockets. It first flew in late 1966 and attained the maximum speed and altitude records for lifting bodies. The HL-10 reached speeds approaching Mach 2 and altitudes greater than 90,000 feet. The X-24B lifting body was a joint NASA and Air Force research project. This craft was launched from a B-52, then boosted to high altitudes by rockets. Body shape alone gave these aircraft the aerodynamic lift needed to fly in the atmosphere. The pilot stabilized and controlled the craft by using its fins and control surfaces. Information from all the lifting bodies contributed substantially to developing the space shuttle. The X-24B proved that a shuttle could return from orbit to unpowered landings on a conventional runway. The payoff from lifting body research started to show in 1977, when the Shuttle Enterprise performed approach and landing tests at Dryden. After it was dropped from NASA's 747, the Enterprise glided to unpowered landings, one of them on the concrete runway. These successful landings were the final step in preparing for the return of real shuttles from spaceflight. Dryden researchers are using an F-111 to study ways of developing more efficient wing shapes. In the natural laminar flow experiment, they modified the plane's outer wing panels. This new wing shape eliminated turbulent airflow over much of the wing surface. Another project geared to improve aerodynamic efficiency was winglets. Engineers modified this KC-135 transport by mounting vertical extensions on its wingtips. These winglets act to increase lift and lower drag. Flight tests showed that winglets improve the airplane's fuel economy by 6%. One of the most unusual and highly experimental aircraft ever tested at Dryden was the Gossamer Albatross. The Albatross was human-powered and pedaled like a bicycle. Dryden researchers added a small motor so they could measure power usage. Construction of the Albatross was made possible only by the latest state-of-the-art lightweight structural materials. The plane weighed just 55 pounds, but had a wingspan of 96 feet. The man who designed the Albatross also built the world's first flight-worthy sun-powered plane, the Gossamer Penguin. The Penguin was a three-quarter scale version of the Albatross, but modified for solar flight by a panel of cells. Electricity from the cells ran a motor, and the motor turned a rear-mounted propeller. One of the most dramatic problems studied here was wake vortex. Wake vortex is a turbulent air condition that forms at an airplane's wingtip. It's caused by pressure differences above and below the wing. The resulting vortex jeopardizes other aircraft behind it. The wake vortex from a large transport can throw a smaller plane out of control and even cause it to crash. Wake vortex became a big threat with the introduction and growing use of jumbo jets. An effort to reduce its hazards became a matter of national priority, and NASA teamed with the Federal Aviation Administration to learn how the vortex works and alter its effects. By comparing upsets of probe aircraft flying in the wake, they proved that using selected combinations of wing flap, spoiler, and landing gear positions, they could effectively reduce the strength of the vortex. Dryden's F-8 flight tested a vital system of the space shuttle. This is digital fly-by-wire, a combination of 3 digital computers with a fail-safe backup computer installed in the plane to control all of its operating functions. Lightweight wires and electronics replace mechanical linkage, and translate the pilot's signals through the computers to the plane's control surfaces. Digital fly-by-wire frees the pilot from details and allows him more time to make the command decisions required by a mission. NASA is supporting the military by testing advanced fighters. The F-15 is an Air Force high-performance plane. Dryden has 2 of these aircraft and is using them in a wide variety of experiments. We are conducting tests with the F-15 to better its engine performance. Our research could lead to new technology in afterburning turbofan devices, in combating stall spin at high angles of attack, and in computerized electronic engine control. The F-14 is a Navy high-performance fighter. Researchers at Dryden are experimenting with its control system to improve its flying ability during combat-type maneuvering. While performing certain extreme maneuvers, pilots have had problems with spin and loss of control. Control modifications done here have made the F-14 easier to fly. For functional versatility, one of the most promising ideas tested here is the tilt rotor. This aircraft is a cross between a fixed-wing airplane and a helicopter, and it has the advantages of both. As a helicopter, it can hover and take off vertically. As an airplane, it can reach speeds much higher than any helicopter. The tilt rotor is powered by 2 engines located in its wingtip nacelles. To make the transition from helicopter to airplane, the pilot tilts the nacelles from upright to forward. As an airplane, the tilt rotor has flown at speeds of almost 350 miles per hour. Research pilots find it easy to fly and very stable in the hover position. Safety is a big feature of this aircraft. It is built with many redundant fail-safe systems, so no failure of a single subsystem can pose a critical threat. The tilt rotor's flexibility and safety features make it highly attractive for both industry and military use. Its ability to hover or put down where no runway exists makes it a likely candidate for transportation to remote locations or possible air-sea rescue duty. The C-140 Jetstar has served as test bed for many Dryden experiments. This versatile plane currently is test flying an advanced propeller model, which should lead to considerable fuel savings in future aircraft. This prop fan is 1/7 the size of the full-scale propeller. Researchers are using it to measure noise levels. The Jetstar performs most of the tests at 8/10 the speed of sound. Designers of future high-speed turboprop airplanes will use the information to design quieter propellers to minimize cabin noise. The Jetstar also test flies the microwave scanning beam landing system used by the Space Shuttle when it returns from orbit. One of the most exotic aircraft ever flown at Dryden is the AD-1. This airplane has a single wing attached to the fuselage through a pivot assembly, so it can swivel to oblique angles. The idea here again is to save fuel. During takeoff and landing, the wing can be positioned at right angles to the body for maximum lift. But as the aircraft picks up speed, the wing can be pivoted to cut down drag and therefore fuel usage. Dryden pilots have successfully flown the AD-1 with the wing pivoted to 60 degrees, its maximum angle. Researchers are studying results of the tests to develop future aircraft using the oblique wing concept. The built-in dangers of flight testing showed up during this evaluation of the PA-30 twin Comanche. Dryden engineers were flying it to study operating problems of general aviation aircraft. The plane had a serious flutter problem, which appeared unexpectedly. Fortunately, the flutter did not cause a catastrophic structural failure, and the NASA research pilot made a safe landing. Another flutter problem that occurred here posed no threat to the life of the pilot. This was a test with the DAST, short for Drones for Aerodynamic and Structural Testing. DAST is a remotely piloted vehicle. The pilot controls the plane from a ground cockpit through uplink signals. This is a cost-saving method of testing highly experimental aircraft. This one proved unstable. Dryden researchers developed a remote piloting technique for aircraft too hazardous to be tested by an onboard pilot. An outstanding example of such an aircraft is HIMAT. Air-launched from the B-52, the HIMAT is powered in flight by a turbojet engine with afterburner. HIMAT stands for Highly Maneuverable Aircraft Technology. From the ground-based remote cockpit, HIMAT's pilot sends commands to computers aboard the aircraft, causing it to pitch. Another command initiates a roll. Highly sophisticated computerized systems on board the craft and in the remote piloting chamber give the pilot as much control as he would have if he were actually on board an airplane. The HIMAT is designed to pull 8 Gs, that is 8 times the force of gravity, in sustained turning flight, while traveling 9/10 the speed of sound. This is almost twice the turning capacity at transonic speeds of any fighter now in use. To achieve such futuristic capabilities, HIMAT designers combined state-of-the-art technologies, including digital fly-by-wire, advanced fighter aerodynamic configurations, winglets, aerodynamic tailoring, and super lightweight carbon graphite structural materials. Once test maneuvers are finished, the pilot uses a television system installed on board the HIMAT to land his plane. When HIMAT lands, it's traveling about 240 miles per hour. One of our F-15s has served as test bed for a number of aerospace innovations. Perhaps its most important contribution to new technologies was flight testing heat shield tiles for the space shuttle. For research purposes, tiles were fixed to the wing and nose. Thanks to these tests, we learned a great deal about thermal tiles and how to attach them for flight in the atmosphere. When the Enterprise performed its approach and landing tests at Dryden, it discovered a problem of great urgency in shuttle landings and in maneuvering of all fly-by-wire airplanes. The problem is known as pilot-induced oscillation, or PIO. It happens when the aircraft's controls don't respond to the pilot's commands as fast as he expects. The pilot automatically assumes the controls didn't get the message, so he repeats his command. Meanwhile, the computer is executing the first command, so the pilot reacts by trying to compensate for the extra command. The result is PIO. To solve the PIO problem, Dryden researchers turned again to the F-8 digital fly-by-wire. For these tests, engineers programmed the F-8's computers to make the plane particularly susceptible to PIOs. The pilot flew the plane in the oscillation vulnerable mode and tried a series of PIO suppression filters to find which one worked best. These F-8 tests produced a good suppression filter for the shuttle, and Dryden researchers are continuing tests with the F-8 to produce workable suppression filters for any fly-by-wire aircraft that may have a similar problem. Flight simulators have been used at Dryden since the X series. They precede in-flight research and enable experimenters to evaluate how a plane will perform under flight conditions. They allow researchers to investigate hundreds of variations before committing an airplane to flight. In the case of the space shuttle, the flight simulator is more important than ever before. This is because the shuttle is such a complex machine. flies in such a wide range of atmospheric conditions, and at Mach 25, travels much faster than any plane has done before. The maiden voyage of the Space Shuttle began on April 12, 1981. A combined blast of solid rocket boosters and main shuttle engines sent the Columbia, the world's first reusable spaceship, hurtling from its launch pad at Kennedy Space Center toward its first orbital mission. The spectacle attracted cheering onlookers and photographers from around the world. Most of the shuttle's fiery appearance came from its two solid rocket boosters. The boosters burned out about 2 minutes into the flight and were jettisoned. They fell back into the ocean and were recovered for use on later missions. The shuttle continued toward orbit, powered by its main engines supplied with propellant from the huge external tank. Astronaut Robert Crippen served as pilot of the Columbia's two-man crew, under Commander John Young. They steered the Columbia into proper orbit by using the Orbital Maneuvering System engines. During the two-day mission, Young and Crippen had a full workload of scheduled duties to perform. After orbit was achieved, the astronauts changed from pressure suits to casual work clothes. This, plus the ability to float freely in the non-gravity of space, made getting around the working compartments fairly easy. Before returning to Earth, however, the men were required to return to their pressure suits, a process which takes about 2 hours. Taking pictures of the Earth was one of the astronauts' duties. Thousands of spectators gathered beside Rogers Dry Lake to witness the first landing of the Columbia. Many had spent the night to ensure a good viewing spot. After circling the Earth 36 times, Columbia was given a go to re-enter the atmosphere. 30 minutes later, Columbia was over Rogers Dry Lake, making its approach to runway 23, precisely on target. And the long-waiting viewers were not disappointed. Thanks to its thermal tiles, it easily survived temperatures of 2,300 degrees Fahrenheit. The first spacecraft ever to land as an airplane was guided to a perfect touchdown by her astronaut crew. It marked the beginning of a new era in which man can travel to space and back using the same vehicle. Commander John Young was first to emerge after landing. Jubilant over the mission's success, he called the Columbia a fantastic flying machine. Within minutes after landing, the machine was being serviced by a convoy support team. Bob Crippen finished his post-flight duties and debarked, following Young, to an enthusiastic greeting by members of the convoy. The astronaut van, part of the convoy, took both men to their post-flight medical examination. The mission culminated at Dryden in a lakebed ceremony. It was a joyful welcome for the astronaut research pilots. after the greatest history-making test flight of all time. Dryden will continue to be a prime mover in the evolution of flight. As aerodynamic innovations are made and experimental frontiers crossed, our people will always be at the leading edge of research.